All right, we're going to talk about data science and racehorse selection, which is my other job. I obviously own part of Trunix, but we also have a company called Performance Genetics, and we started that in 2011. And so for the last 7 to 8 years, I've been gathering a lot of data on racehorses in different ways. I'm going to show you a lot of that. Happy to show you it because it would take you forever to collect the data that I've collected. So we'll talk about just the challenge of using data science and but why it's important in racehorse selection. I'll talk about what I've done to date, what has worked and what's been a complete disaster, and what we're trying to do in the near future to increase our odds of selecting faster racehorses. So this is probably pretty essential for people to understand from the viewpoint of anything to do with yearling selection. There are only 4 outcomes that you can possibly have at the yearling sale. You either have your true positives, horses that you thought were fast that turned out to be fast. I can remember, clear as day, Black Caviar standing in front of me. Couldn't forget it. You couldn't forget it. I couldn't forget a bunch of good horses that stood in front of me. How they looked and what they did and how they walked and all that sort of stuff, I've just got it in my mind and I remember what they looked like. The true negatives, horses that I thought were slow that actually turned out to be slow, I don't remember them at all. They were just slow. I don't care. And that's the thing. We tend to remember the horses that we liked that turned out to be fast, but we tend not to remember the horses that were slow that actually turned out to be slow. Because it's sort of like, oh, well, I was right about that, I don't need to worry about it. So we move on to the next horse. Here's the kicker. The 2 that we learn the most from are the hardest to learn off. So the false positives, horses that I thought were fast that turned out to be slow. I tend to rationalise those in my mind and sort of look at them and say, the trainer broke it down, or they ran it over the wrong distance, or they did that. Everyone does that. Very few people have a very well constructed system that has a feedback loop to help you learn. And then obviously the false negatives, horses that you thought would be slow that turned out to be fast, they're even worse. Like, you sort of like want to hide and sort of say, oh no, I didn't get that wrong. But you do. And they didn't beat anything on the day. There was a wet track over a distance. How am I supposed to find a wet tracker? Who cares sort of deal. So rather than learning why it was, fast or slow, you tend to discount. Now, the irony is, the ones that you want to learn the most of, in terms of learning how to increase the number of true positives, which is what we're trying to do, are the hardest to learn from, the false negatives and the false positives. And the other thing is that it takes years. So we look at a yearling and it's not until 2 years later that we actually know what the outcome was. So the time difference between that, your brain just switches off and doesn't even think about it. And this easiest person in the world to fool is yourself. So that 2-year gap is a learning loop that is too long without having some reference or some way of establishing this is how we should gauge how good a horse is and what it's going to be. And this is not just us. Like, I know there's a couple of vets in the room here. This is no different to when you're looking at an X-ray or looking at a scope of a horse. You tend to forget the horses that turned out to have something wrong, and they've gone up to wherever and you haven't seen them. You just discounted in your mind the influence or what that factor was or what that variable was that made that happen. The really thing is what we need to do is learn how to increase our understanding of false positives and false negatives, and it's really hard to do unless we have a system in place that actually manages that. And this is why it takes the average agent or trainer years to work out what to look for in a horse. It's a constant observation and feedback but it's 2 years later, so you're constantly going back and looking at all these horses. And even if you're a farm manager and you're looking at horses every day, you still have a cognitive bias and you do forget those horses that you thought were good that turned out to be slow. So here's a sort of how do you measure an outcome. So here's a hypothetical population of say 4,000 yearlings, which is close to what we have at the September yearling sales. There will only be 120 of them that are any good, which is really low. 3,880 of them you wouldn't want to feed. just don't want anything to do with them. So the average bloodstock agent or trainer will select about 10% of the population. They'll have a short list of about 400 horses at a sale with 4,000 yearlings. But from that, they'll have two outcomes: precision, or strike rate, and recall. So the precision is basically 10% of the 400 horses they selected, about 40 turn out to be good. That's considered quite good by most industry standards. The recall is actually 33%. That's actually pretty poor. Of the 120 possible elite horses, they found 40 of them, missed 80. That's actually pretty poor. And so that's what in most guys that come in and they look at a lot of data and stuff like that, and we've got different guys who I've worked with, Chris Long, who works for the San Diego Padres and Liverpool Football Club, he does data science for them. They come in immediately and say, this is disgraceful. I can't believe these guys are that bad. But it's hard to be better than it. So the challenge of data science in this is that the positive case is very small. You can use some things like synthetic oversampling, which we can do in terms of data science, but it's a challenge unless you have a lot of data. So if you want to measure something, you need to measure a lot of horses, and there are a lot of different ways to be a good racehorse under different circumstances. So when I say that 3%, when you break it down, as I said to you before, there's a big difference between JJ the Jet Plane, American Pharaoh, and Yates, who wins the Ascot Gold Cup. They're three totally different horses. They ran on different surfaces, different racetracks, and they won. So there's a lot of different ways, and this is where I made a big mistake. I think other people, mentioned before the genetics. I think a lot of the companies that have come out with genetic products have made a mistake. I've made it, is you cannot do every horse. It's just not possible. There's too many ways of being good in different ways. I was here with Kevin there earlier on, and we went to races at Kenilworth, and they sit and they wait and they wait and they wait, and they get the turner and they ping and they go. Well, that's almost unique to anywhere in the world. They don't do, Australia's a little bit like that, but dirt racing in America, they go from the gate, they're gone. So physiologically, it's a totally different animal. So a lot of these things are that where you need a lot of data, but I think that the best answer is actually, I talked to and Max Rothschild was the first one. He said, I think you can be really good at predicting one horse, one type of animal. If you got really good at it, you could actually make it more predictive to do one animal. And the interesting thing about that is, and I'll talk about it a bit along, the ends of the population are much easier. So sprinting 2-year-olds, early maturing 2-year-olds, because they've got physiological advantage early, they're easier to find. And the long distance horse is easy to find. The ones in the middle, good luck. They're hard. So the data also learns very quickly if you have homozygous or homogeneous aspects to it. So if I test all horses and I already know that they're CC sprinters, say for example, then that is fixed. So the data you can look in the data for other aspects which tell you why this horse is fast or why this horse is slow. So that's a very key thing, is that if we're looking, when you want to look at one type of population, you start to fix as many variations as possible. Later on, there's a variation that's to do with height in a horse, and it's right basically next door to a variation to do with laryngeal paralysis. So when you're sort of selecting for height, you're selecting for one of the variations in height, you're selecting for laryngeal paralysis. But what you can do is take all CC horses that are all certain size, and when you start to break that down into those sorts of subgroups of populations, you start to get much better at working out what is fast and what is slow. So the other thing which is also interesting is when you start to gather a lot of data is that if you're specifically looking for elite sprinters, finding I've tested Justify as a yearling, finding him is as important as finding a slow horse, because what Justify, who's an elite miler to 10 furlong horse, is actually tells me more also for the elite sprinter, because it can separate them. It can say, we know what Justify is, an elite horse, but he's not an elite sprinter. So finding those good horses in different categories is almost as good as finding slow horses. So how many horses are required to make a good model, also known as how many are in your database. If we're selecting for one type of horse, 600 horses is what you need with known racing outcomes to make an algorithm with 95% confidence. And this is talking about measurements, phenotypic measurements. 1,800 horses with known racing outcomes is to have 99% confidence in what you've got. For known racing outcome, I mean you need to have at least 3 lifetime starts. Things that have 1 start, 2 starts, not interested, because there's too much evidence that something could have gone wrong. Like you could have a filly that starts and she has 1 start and she's blazingly fast and chips a knee in the first start. Don't know if she's any good or not, so you don't have any evidence. Once they get past 3 starts, it's because it takes 3 starts to break its maiden on average, and 7 starts to win the stakes race. And on average, they're 3.5 before it wins its first stakes race. So we take 3 lifetime starts, 4-year-olds and older as when. So when I'm taking a lot of data, it takes years for it to come to fruition. So I take a stack of data and I gather it all, and I have to wait a couple of years before I actually can use it. So what have I done and what have I made mistakes? We'll talk about data modelling. That's quite interesting. We'll talk about equine genetics. Someone spoke earlier about that, and I agree with a lot of what they said. Within that, we'll look at genome-wide association studies and mitochondrial DNA. We'll look at cardiovascular measurements, and we'll look at biomechanical measurements about how we're doing. So 2 overall things that need to be understood. You should only measure what matters. So if I have 2 variables and they're highly correlated, well, I don't need them both. I just need one. And what I'm really sort of interesting is it doesn't matter what it is. If it's a DNA marker, cardiovascular measurement, biomechanical measurement, whatever it is, as long as it's explaining the biggest difference between a fast and slow horse, I'll use it. And I can use it in the field. So when I say I can use it in the field, I can't get yearlings up on treadmills and do I can't take a muscle biopsy because people won't let me take. I can't take blood at yearling sales in North America because once you put a needle in that horse and the horse walks out and the guy looking at the horse sees a little blood mark, they're like, what have you put in that horse? So you can't do a lot of things. You've got to do a lot of things that are non-invasive, so there's a limitation to what you can actually do. So here's the data modelling we did. We got the Jockey Club data, and we looked at over 40,000 yearlings. This sort of ties back into this Trunic stuff, which we talked about a little bit earlier on. So we just looked at the performance data of a racehorse, and as a racehorse, the sire, the dam, and the 4 grandparents. That's all we got. So we got how good was distorted humour as a racehorse, how good was he as in terms of his production of stakes winners, how good was he as production of stakes winners as 2-year-olds, all sorts of things like that. The target variable, what we were trying to predict, was binary. We said they're either fast or slow. We used a combination of things to make them. First of all, we took all the horses that were stakes winners and greatest stakes winners, and then we used the Jockey Club, what we call, they've got a value called the CPI, which is a measure based on prize money, which we think is quite good, not perfect, but quite good at telling whether or not you've got a good racehorse or not. And so we use XG Boost, which is the machine learning algorithm that we used. And so we trained a model on 40,000 yearlings. And we went through it and I kicked out a whole lot of stuff and said that's irrelevant and this, that and the other. But what it come down to is that we then took the 2012 yearling sale, Keeneland September 2012, and there was 3,602 yearlings. There was 127 of those that were subsequently elite runners, and our trained data model selected 412, which is a bit over what, 11% of the 1.5% of the catalogue, which is a bit more than what the 10% an average agent would do. And its precision was 14.3%, which is better than an agent. So if the average agent's doing 10%, we could actually just with data alone get 14%. The recall was 46.5%. So we still missed a lot of horses, but just the data modelling itself was good enough to predict out a high precision in a big, that's a big sale and a big sample of a sale. What were some of the variables that were affecting outcomes that used in the data model? Race performance, as I mentioned before, is key. It's underrated. So I can tell you now that the one thing which I'll talk about, which I should mention, stallions. The bar for stallions has got really high. So to be a really good stallion now, to come into South Africa or Australia or anywhere, the variation between in terms of racing outcomes is smaller and smaller and smaller. You're getting very good horses coming out here to be stallions. So when you talk about the outcome of the foal, the variation occurs in the mare. So what they're being bred to, because we don't care. The mare can be unraced, unplaced, placed, all that sort of stuff. So when you start to look at populations and start to do this sort of data, the biggest variation occurs in what the mare is in terms of your outcomes. And it's difficult because there are certain ways of measuring racing class. For example, in North America, there is very little difference between having a good allowance winner at Belmont, at a major racetrack like Belmont or Keeneland or that, and a listed winner, and the outcomes of the foals. Very little difference. So a lot of that commercial stuff that we look at in terms of what sells, you can actually sort of work your way around. But the racing performance of the sire and dam is very much underrated. In the racing performance of the broodmare sire was important, especially when the dam lacked performance. If the dam had one start or two starts or was unraced or whatever, the broodmare sire had some importance there because I guess what we talked about a bit earlier, you know, those really good stallions impart more of their genome into the broodmare sire, they put more into the daughter. Definitely race performance of the Grand Dam. The foal rank 1 to 6 was much better out of the foal, so the first 6 foals out of the mare was way more significantly related to performance than the rest. The crop number of the sire, which was, I'll get to showing you there, and the performance of the sire and the sire's 2-year-olds and the generational interval. It was more profitable in terms of outcomes to breed a young mare to an old stallion, or vice versa, an old mare to a young stallion. Don't know why. Works out the data like that. That was just one of those things, and that's almost like a rank of what importance. So race performance is obviously way more important than the generational interval, but these were the factors that actually influence the performance. So this is one of the things that when we started to look at that data, we sort of say, okay, well, how does that actually work? We got the Jockey Club data, and we asked them to look at it all, and they gave us every single foal, and by these good sires, we had a ton more than that. Obviously, that's all I could fit in. But this is the crop number, and the shuttle crops were counted separately. Like, so for Royal Academy, this is Royal Academy out here at 30 something, because he went shuttled between Australia and then US and various places. But you can see what happens is over a linear period of time is that it just drops off. Why this happens? I think it's both a combination of age and frequency. So I think also what happens is how frequently a stallion, like these shuttle stallions, are pretty savage because they're breeding a lot of mares. I think that there must be some sort of epigenetic thing going on in terms of, and I'll give you an example of it. One of the stallions we had when I was at Arrowfield was Snippets, and when he was 16, he got, like we obviously breed the same in the Southern Hemisphere, same thing, he got sick over the winter time, and he looked awful, absolutely awful. And he had 120 mares to breed to him. We bred them all, but it was like, you know, it was really tough to get him to breed the mares. Like, he just wasn't well the whole year. He had and this is a stallion that was an 8% stakes winners to foal stallion, reliably. He was a very good stallion. He had we had 94 foals or 92 foals or something like that, and he did not have a stakes winner. So that year he was sick. And he was getting better mares. Like, he was 16 years of age, he was getting the really good mares. He was standing for 30,000. We were getting, you know. So there is an effect there, an epigenetic effect or something that occurs as these stallions age, whether it's the fact that sperm is a replication, like with mares it's not a replication, with the eggs already there and they come out. With a stallion it's a replication each time. I think it's slightly underestimated how important the environment is. It's no different to when Sadler's Wells got sick that year. He got sick up there in Northern Hemisphere, and he didn't fire as many stakes winners out. Here is what happens, and this is despite the fact that this is the mares, the quality of the mares as runners. So the average CPI, which is a measure of racehorse performance, these are the mares that are getting bred to these stallions. So in the first couple of crops, they're reasonably good, and then all of a sudden when they get good, these stallions, like when you start talking about, you know, these stallions as they're getting older, they start serving better mares. But this is the outcome of their foals. It's no better. So what happens is even though they're getting better mares, they don't get a better outcome on the racetrack. Now this is the mare. So this is on the other side when I said it was foals 1 to 6. So If we look at here, this is the average price at sales price at Keeneland, which is this blue line here. And so when we start to look at these foal numbers of these mares, once you start to get these mares here, you see it's coming up. Well, what that is, these are foals that get into Keeneland, like that are in these good sales. They're on their 8th, 9th and 10th foal. Well, in foal 1, 2, 3 or 4 or 5, they've already had a stakes winner. So people start paying for residual value. But this is the race performance, this red line. They don't get any better. So this thing of residual value is a bit of a myth to me. I think you are better off taking a younger mare, and I'll show you something a little bit later on. That people pay that because it's a safety. It's like bloodstock agents go there and say, I can buy the thing that's a half to a stakes winner, and I know if it's no good, it can still be bred from. And I think that's what happens. We tend to pay a little bit too much for residual value of foals, but and then once they get off to the foal 13, 14, 15, you start to talk about the race performance and the correlation to price matching back up again, where people realise that these older mares aren't going to do it. So what did we learn? So even the best stallions have a decreasing production of elite runners after crop 5 or 6. The first 3 crops of the stallions are always the best. Doesn't matter how bad they turn out to be as stallions. The first 3 crops will always turn out to be the best. And the best mares' best foals are usually the first 6 foals, and I think we overpay for residual when compared to subsequent performance. So one of the little neat things we found was this group here. One of the best pockets for play, and this might not apply to South Africa, but it was pretty compelling in North America, is for buying value in the sales rings is fillies to make the page. They have to be stakes winners, otherwise it's absolutely nothing. And so we look at fillies only, where the fillies dam is a winner, unraced or placed, but had less than 3 starts. But they're half sisters to graded or group stakes winners, but not out of stakes winners. So it's a very thin pedigree. The producer, she hasn't produced a stakes winner herself, so the filly isn't a half to a stakes winner, and it's the first 6 foals out of the mare, and it's a good class broodmare sire. You constantly underpay for these fillies all the time. Underpay. You don't pay nearly as much as you should do relative to those horses, those fillies that are out of the half to stakes winners, and they're the 10th foal or something like that. Here's a good example here. So this filly here, she's by City Zip, who's a good stallion. The mother is a half to a good horse in Persistently, a Group 1 winner. She's only had the 1 start. I actually asked Bernard McCormack, who bred this filly here, fractured her shoulder at her first and only start. This is the first foal. This is a good example here. So this was a $40,000 yearling by a client of mine, friend of mine, Jason Litt. And that's the pedigree. And so she was in book 2. Like the average in book 2 was, what's that, Stu? Book 2 averages? 150? Yeah. So she was well under. But she had a good size, she had a few things going there. All right, so she won a Group 3 race, and she was Group 1 placed, and they sold her for $1.45 million. And he's done it a few times. He bought Scherschinger. He's bought a lot of horses with that exact. So you see, she's made her pedigree right there. She is the stakes winner. That's her production. She's in Fodder Curlin. She's nothing really jumped out of that pedigree. Like if you go back there, it's not like there's some big, massive update. She's made the page. But you go from a $40,000 yearling to $1.45 million. That happens. That is a better play than buying the 10th foal out of a mare that's had a single stakes winner, in my opinion. So we'll talk a little bit about equine genetics. I'm sure there's a lot of you have already sort of gone across this and understand it. I'm sure Equinome or someone else has come out here and chatted to you about it. Obviously, the equine genome was sequenced in 2009. We've had, the initial one was an inbred thoroughbred. So a lot of the genetic sequence SNPs now, a lot of the changes aren't to do with actually thoroughbreds. They're to do with other breeds. And one of the big things I say is DNA is not a destiny for outcomes. Trainer effect is quite large, and how the horse is raised is quite large. So don't think that just by pulling DNA you can tell. A SNP's just a genetic change there between at a certain locale, at a certain point in time there's been a mutation that's usually found through selection pressure or something like that. You've basically horses going from one place to another, they have a selection pressure and there's a mutation that occurs. What other genetic changes have an effect? There's an epistatic effect, so you can have a change in one part of the genome and it has a change in another area of the genome. This is why I think they talked about it at the meeting in Korea there about gene doping. We do not understand right now what the effect is. So if you went and changed a horse from a TT on myostatin and all of a sudden made him a CC, we got no idea what the cascading effect would be on other genes. So you just can't, at this stage, we just do not know enough about what happens when you make changes, or what are the regulatory effects of changes in DNA. Epigenetic effects, which is what I've sort of briefly talked about with those stallions, and how you raise your foals, and what foals getting sick and various things like that. Some of them overcome it, some of them don't. Epigenetic is the environment on the DNA. So how you feed your horses and do all those sorts of things, which Stu mentioned, has an effect. And we can talk about nuclear mitochondrial DNA. So we did a genome-wide association study where we took fast horses and slow horses at 670,000 SNP panel. Basically, there were 250 SNPs, or changes in genetic code, that related to the difference between fast and slow horses, and about 25 of those, which is a small number, were really highly relevant. We checked then elite sprinters. We did all the CC horses, and we looked at elite sprinters and non-elite sprinters, and using the same panel, and there were about 8 further SNPs that were highly relevant. So you're not talking about a lot of difference in terms of, which is why I believe it's just too hard to pull DNA and say this is a fast or slow racehorse. It just doesn't work that way. The other aspect which is worth talking about is the mitochondrial aspect of this. So mitochondrial DNA you get from your mother. I got it from my mum, but I can't pass it on because I'm a male. Okay, so it's all female related. So it goes up the bottom part of the pedigree. All women have it, all females and mares have it, and they pass it on to their foals. If they're fillies, they'll pass it on again. So it goes uninterrupted across the female line. You don't, so I can't pass it on, or I can't pass on to my kids. My wife has given it to our kids. So why is it important? So mitochondria is a respirator of cells. So it makes the cell breathe. So when you start talking about muscle, that's very important. But mitochondria is small. It's only 16,000 base pairs. It's a very, very tiny piece of DNA. And what it needs is nuclear DNA to do the work. So one of the things which we're working on right now, which is, I think, where we're going to end up. And it was alluded to before. So what we're seeing now is nuclear DNA interacting with mitochondrial haplotypes. And I'll show you a mitochondrial haplotype, and you start to see. So when you look at your pedigree page and you look down at the first 3 dams, and you see a son of Mr. Prospector's had a stakes winner, and another stakes winner in the pedigree in the 3rd dams by Mr. Prospector, and a 3rd one's out of a grandson of Mr. Prospector. What that's telling you is that Mr. Prospector in the nuclear DNA is interacting with the mitochondrial DNA. And that's where the elite horse is coming from. So you'll see that. I'm sure there's guys, you sit there and you look at your pedigree page and you say, I'm mating it to, Captain Al or whoever it is, or it's VAR because there's a stakes winner, there's 3 stakes winners by Sons of Stormcat, and there's another stakes winner by a Son of Stormcat, so I'm going to send my mare to VAR. That is actually a sound approach, because of what we're starting to find out in terms of mitochondrial DNA. So there's an interaction between the nuclear DNA, what you get from your sire and your dam, with the mitochondrial DNA. So when we sort of look at pedigrees, that's what I'm saying, is that one of the other considerations which we're bringing into TrueNix, and which we're going to bring into, is looking at what has happened in terms of what nuclear parts of the pedigree are actually interacting with the mitochondrial haplotype. So now there's an interesting thing. We know that there are only 3 stallions. If you trace every stallion back, there are only 3 stallions in the whole Y chromosome. That's it. I wish Charles Fall was here. This is the best part. So there are only 18 mares that the thoroughbred breed traces back to. 18. So here's one. So this is a mare called the L haplotype. This paper back here, I should say, what they did was they got all of the breeds, different breeds, and they did their mitochondrial DNA. And because it doesn't change, because it gets passed faithfully on each generation, you can actually work out where it's all come from. And so in the thoroughbred, there were 18 families. We found the 18th family. The colonial family in Australia, colonial family number 2, I think it is, with Capitalist, is actually the last of the mitochondrial families that we found. Up to that point, there was thought to be 17, but there's now 18. So what we do is we trace it back along a female line, and so what we get back to is this is the L haplotype, which is just a sort of way of classifying it. And so this mare here would have been 10,000 years ago, maybe longer. These mares here, which are subhaplotypes because they would have had a slight genetic mutation in the mitochondrial genome, they're subhaplotypes, and we make a further subhaplotype here. So this mare here is the looks like the L3, is it? Yeah. I'm going blind, but that's the L3 subhaplotype. So all of these female families, which you see on a pedigree page in terms of the 1U family, the 9C family, the 6A, the 5B, 5G, 4A and 1A from Bonnie Lass, they all go back to the same mare. Okay? It's a lot of that. So when you look at 6 cross pedigrees and they say it's from the 12A family or whatever it is, there is a mass of them. So the L haplotype, the N haplotype and the M haplotype have most of the thoroughbred breed. There's a couple of obscure ones, but this is basically why a lot of the relationships that people come up with on pedigree pages, and they say, oh, you know, this family goes with this family, or they see structures within pedigree pages, is because right back here, they're all actually the same mare. They just didn't know it. So a lot of the stuff that I had dinner last night, I don't know if any of you else have had dinner with Charles Fall. It was an experience, let me tell you. Charles was going on about all these families, and the 6A family is one of the ones he mentioned. He started talking about this, you know, the 6A family and this, that and the other, and I knew that this is basically all one thing. Here's the one here, this one here, you'd know this mare, she's a Dame Monsieur. So there's a fame, like that's what goes on the Monsieur. So that's actually a mistake. The 1U family should be the number 1 family, which is the N2 haplotype, La Troyenne and Go Webb and all of those. This 1U has a mistake in it. So somewhere there's been a foal swap, or somewhere someone said this is the foal and it's not really the foal. So we've gone through, we've done about 3,500 broodmares in various families. We are just about ready to publish this out, and this is why you see this variation and why things don't quite max up, and why we're trying to get towards is try to work out with these matings is how this all works properly. I mentioned this before, so this was another interesting study which I thought I'd mention on the genetic side of stuff. So this was 2 studies actually. One here was Samantha Brooks is in Florida. She's a very good equine geneticist. They did a study back in 2014 where they looked at growth and laryngeal paralysis in in thoroughbreds. They located it down to the biggest one that explained the most was on chromosome 3. And it is a genetic change on chromosome 3, and it is independent of heights. What it means by independent is that it's inherited independently. So it's still linked, as in the 2 of them are very close together and they sort of move together, but they are independently. So that is something we've actually tested for. You can actually do a test for that as a yearling, so we can actually test for that. So in terms of genomic predictions, very good model for predicting large populations. Like you can actually, if you had hundreds of horses, you could actually do a really good job with it. It's a good negative predictor of individuals within that large population. But overall, because it has to generalise and everything goes into buckets with DNA, it's very hard to tell the difference between JJ the Jet Plane, American Pharaoh and Yates. It's just not as cut and dried as they'd like. The false positive rate and false negative rate's too high. So that's I've made that mistake. We've spent hundreds of thousands of dollars trying to get it. It just doesn't predict out as well as you'd hope. I wanted to show you this because I thought this was really neat. So we've been testing this, and some of the vets would probably be interested. This is a real-time PCR thermocycler. This company Byron is putting it out. We're actually tested. We've been doing this little single nucleotide. We've actually been testing it on this machine. And this machine, if you can actually see, it's a phone. It's a mobile phone. It's about as big as that. Like, it is tiny. And you can do PCR, real-time PCR, and it costs $4,000. You can do about 6 snips in one go. So you could do, if you're doing one snip like we do, we could do 6 horses. But yeah, it's possible to do all that sort of stuff. Moving on, almost finished. Cardiovascular testing has been around for a long time. Dave Lambert did it in the 1980s. When M-mode ultrasounds became very good, he still tests today with equine analysis systems, EQB, DataTrack, Equix, Performance Genetics, which is our company, all use it. It predicts about 22 to 20% of the variance in the performance of thoroughbreds. It doesn't do any more than that. Again, it's probably very good for a negative prediction. It's very good for horses that are wanting to run a distance, although very top-class sprinters tend to have a good cardiovascular system. We also looked at measurements of the spleen, which we do. You can actually do that if you wanted to, but we found that there's actually a DNA marker that's actually better, explains more of the variation than doing the spleen. All right, so this is the heart. This is the left ventricle of the heart. This is it beating away here. Okay, you see that one? It stops for a second because it's a loop. So it's not because it's a 10-second loop. All right, I'm going to give you that one. You've seen enough of that? All right, can you play this one? Give you another few seconds with this one. All right. These are both 3-year-old fillies in full training. They've got a similar body weight. You know, they're similar sized horses, similar body weight. Any guess which one was the better one? All right, come on. Which one do you think was the better one? Huh? She said the second one, you said the first one. Okay. This one here, which was the first one, this filly had 9 starts. She won 6 of them. She was the winner of the Frizette Stakes as a 2-year-old. She was a Grade 2 winner at 3. She was a very good race mare. This mare over here had 9 starts and couldn't win a race. All right. So here's the variation you're looking for. So that's the cardiac wall there. So we're basically taking, I'll show you exactly how it works. So if this was a heart, and what you're taking is you're taking an ultrasound and you're taking a beam which would be slicing across the heart like that. Okay, so everyone sort of understand that it's just a beam, one part. So the representation of that is that would be like the walls, the wall around there, and the internal diameter would be the internal part there, and that's the internal diameter. That's the heart as it's right open up there, so you can see. So what you're looking at and why is there the variation between those two horses is this is a representation. So it's just a beam going once across, but it's actually the whole cardio that you're making an extrapolation of. So this is a very strong wall here. You got the internal. I'll just do it over here as well. That's a very strong wall there. That's the wall there. She was a sprinter. She was a sprinter miler. She was an on pace, and you've got a lot of distance from there to there. And it's round. We call it a bullseye cardio for a reason. It's round. This one here is like a V. Looks like a heart, but it's actually a sort of anyway. They do not have enough cardiac capacity. There's just not enough blood going in. Now, occasionally, this is why it's not perfect, is occasionally with these horses, they can be slightly bigger. And if you've got a super efficient runner, like if this thing does not make, like it just walks like a panther and it gallops out and it's got a perfect stride, you can get away. These horses can make an idiot of you. Most of the times they don't, but they can make an idiot of you because they don't need the cardiac capacity to be a good racehorse. They can just get away with a good stride. So very, very rarely, but this cardio here is way more predictive. And what happens is you actually get what's called symmorphism, which With that cardio being that size, you end up with a lot more horses that have a lot of other features like a large girth. It's an interesting thing there. So everyone looks at a girth and they say, oh, that horse has got a great heart girth. It has a very low relationship. The heart girth actually has a low relationship to the heart size. What it has a relationship to is lung capacity. So when we put a whole lot of horses up at KER in Kentucky with Joe Pagan, we put masks on them, we measured their girths round and we measured their body lengths, and those horses with bigger girths and slightly longer bodies had more lung capacity. So you're probably selecting for the wrong thing there. But so heart scores have been around for a while. They were in the measurement of the QRS interval was used in the 70s and 80s. Dr. Steele and those guys came up with that. The M mode measurement, which was replaced in the 90s and 80s and 90s, is a much more significantly, it's a better technology. Traditionally we use the measurement of the left ventricle. We measure the cardiac wall, the internal diameter. But the traditional measurement often fails to capture the full quality of the cardio, as it's time and space. You saw that cardio as it was moving. You could see that it was large, but you could also see how it's moving. So you need to capture that in some way, which is what we're working on right now. So the way we've done that is we've used image recognition. So one of the big fields at the moment is image recognition, the ability for driverless cars to go down the road. We've used that same technology to look at cardiac parameters. So the image recognition stuff, ImageNet was trained on 13 million images. And what we do is we take those algorithms and we train it on cardios, and you could train it on anything. We could do x-rays, we could do anything if we really wanted to. So the first competition for ImageNet was an accuracy of 73.1%, and now we're at 97.5%, almost 97.5%, which surpasses human capability. So if you give a human a whole lot of different images, they make more errors than the best of the image recognition programs do now. And video is just a representation of image. If you have a 10-second video and you've got it at 30 frames a second, you've just got a lot of images coming in front of you. You've got 300 images, so you can use that as data, which is what we did. We used 600 elite horses and 600 non-elite horses. So we have 360,000 images or 360,000 data points to use, and we trained a deep learning neural network. How it works is exactly that. It breaks that video you saw down into frames. It's one frame, frame one, frame two, and we train two neural networks. One is to look at to see if any of those give you a representation of a good horse or a bad horse, and the other one is to look at the difference between image one and image two, image one and image three, image one and image six. So we can do that. So what's the outcome? The outcome is if we use a traditional method and we use a random forest and we train it on 1,800 yearlings, the best model that we can create has an accuracy of just short of 70%. If you could imagine a coin flips 50%, 70% still pretty good. Traditional measurement scaled to body size, which is important. So cardios are like engines in a car. You put a big cardio in a small car, you break it down. You can't get that. At the end of the day, the cardio is a muscle. You've got to get it fit. So you can't work that filly that has a big cardio. You cannot, and she's small, you can't work her hard enough to get that muscle fit. You end up tearing her apart. But if you scale, so we scale the cardios to the body size, it improves the model to 73%. Using a deep learning neural network that we use cardio video and biometric measurements, we can actually get it to 82% because of the fact that it's better at us as humans at identifying variation in images. So unless I feed it specifically biased data, it will better understand and deal with how to best balance data and how to get the true positives and reduce the false positive and false negatives. Here's the hit, but here's the little catch. The better it gets, the closer it gets to the ground truth, and the ground truth is only 3% of horses are any good. So the better it gets, the less commercial it gets, because I'd have to go through lots and lots and lots and lots and lots of horses to find the 100. For every 100, I'm only finding 3 that are good. The closer it gets to actually the reality of the test. So the data, I should say. So it's ultimately uncommercial. So it's very, very hard to make it into a commercial sort of outcome. Here's the final thing I want to talk about was biomechanics. So this was a paper here that was written just a month or so ago, April 9th, by Alexander Mathis from Harvard University. So he used what he did was he took the video and he broke it down into the frames, and then he put dots on each frame. And then he trained an artificial neural network to put the dots on himself. So instead of him having to hand put on dots anymore, he's got an artificial neural network that does it. And he's been doing it with mice, and he's been doing it with fruit flies and all sorts of stuff. And so I contacted him, and he said, yeah, let's go and do some horses. This took a while. So we took 10 different videos of horses walking in different circumstances. So you had to have horses walking into shadow, out of shadow, walking, different ways, and we had to do different coat colours. So we had to do grey horses, bay horses, chestnut horses, brown horses. There's a difference between bay and brown horses, yeah. And we shot it at 60 frames a second, and so for every 10 horses for 4 seconds. So we had 2,400 frames, and I had to go through and annotate them all like this, which is a pain in the ass. But then we trained it on 40% of the data, and we let it and tested it on 60% of the data. So we only trained it on a fraction of the 2,400, and we tested it back. And the error rate between where I had put that marker and where the neural network thought the marker should go was less than 3 pixels, which is nothing on an image. So I'll show you this. If you press play. And we end up with this. So on the left-hand side, you've obviously got the horse. Oh, play it again if you can, don't mind. It should have been a loop, but it's not. On the left-hand side, you've got the horse walking by, and on the right-hand side, you've got all those dots and those images. And so what ends up happening is that we end up having data for each horse. I'll go forward anyway. Every sort of joint then has a data. So we end up with a signature for each individual animal as it's walking by. So over a period of time, we get the data set. We can actually group horses judging by the way that they've walked. Now obviously we've got to make sure we give every horse 3 walks, so we get a fair chance for them to walk. I asked Stuart if they're on bute for sure. So we've got to get a fair representation of the horse, but that's where we're heading. So this stuff here, this last piece of slide that I've just showed you, we haven't completed that, but that's where we're heading. And what we're hoping to be able to do is sort of, because that is the first filter that everyone uses at a yearling sale. Everyone goes and looks at horses at a yearling sale. And that's what we're trying to get towards, is sort of say, more consistently say, this is what this type of horse is, and this is what the functionality of this horse is. And so we've got, once you get a lot of data, you'll be pretty amazed at what's available in terms of artificial intelligence and machine learning programs, models that can be built. It's just a matter of getting a lot of good data in there and trying not to bias the data. So, so the same process of what I've already done with the cardiovascular parameters is what I'll do with the markerless biomechanics. And we've got 1,300 yearlings and racehorses, so we're going to be reasonably happy. I mean, I'd love to be 1,800 or 2,000. But then I could also use SciCam or any of these other people that take video. I could actually just scrape their data and use it. And as I say, the overall goal is to find a sort of similar type of horse. We're not actually trying to find what's good and what's bad. We're actually just trying to say this is the group of horses that they fall into. So my work for yearling inspections, buying racehorses, is probably going to be looking at horses from the data model and go and look at them and kick out horses with obvious flaws, and then use this video recognition to identify horses of the same signature, the same way of going, on the hope that that means that then when I go and do the cardio, or when I go and do the DNA, they're all CC horses, or they're all of the similar type, and that's what we're trying to get down to, because you cannot do every horse the right, you can't, it's just impossible. So that's where we're heading towards, and we test the DNA, which is just a hair sample, and the cardiovascular parameters for these horses.